Okay, so it's a shear stress problem, but before we get there we need to work out where the centroid of this section is, and also we need to calculate the value of the second moment of area of the section about a particular axis, which is an axis which goes through the centroid, but which is parallel to the z-axis. And the reason that we're interested in particularly that axis is that this section, so it's a T section which is part of a beam which is coming in and out of the page. The section is carrying a force, a shear force of 80 kilonewtons, so that's as if the bit that's going into the page is trying to move upwards and the bit coming out is trying to move downwards. They're trying to move past each other, but the section is made of a material which is strong enough to prevent that, and the section is holding altogether a force of 80 kilonewtons, we're saying here. So what we're trying to find out excuse me, is how that force is distributed over the section. It's distributed as a stress. The stress is the manifestation of the force over the section. It's a little bit like a direct force, an axial force. It manifests itself as a direct stress, which is evenly distributed over the section, so we just divide force by area to get stress. But in this case the distribution of stress is a little bit more complicated, so it's not just as simple as saying divide the 80 kilonewtons by the area to find out how the shear stress is distributed, because well, because we know, for example, that the shear stress on the top and bottom, let me see if I can shade those in. So up here, top of the section, at the bottom of the section, the shear stress is 0, and we also know that somewhere around the centroid, and here somewhere, the shear stress hits a maximum. So that's eventually what we're trying to find, and the steps on the way are to find where the centroid is, and well, I could probably make a pretty good guess that it's in here somewhere. And to calculate the shear stress distribution, we'll need to find out what the I value is about an axis, which we'll call ZZ, which goes through the centroid. So let's start off by redrawing that shape. I'm going to find the centroid by treating this T shape as being composed of two rectangles, because there's a way to find the centroid which exploits the fact that we know where the centroid is of each of the component parts. So we're trying to find the centroid of the T shape, which we by instinct know is up here somewhere. Remember, the centroid is more or less the same as the centre of mass or centre of gravity. It's the point, if you were to have cut this shape out of a bit of metal, you know, if you balance it on your finger, that's where it would rest horizontally. So we're trying to find y bar. The way we're going to do it is from knowing what the where the centroid is of each of two well-known shapes. So we know where the centroid of those two rectangles is. We're going to define those with respect to an arbitrary line, another arbitrary axis down here, and we're going to say that we require that the first moment of area of the whole shape about that axis, about the red dotted line axis, is the same as the sum of the first moment of area of the two rectangles. Might be worth pointing out that a property of the centroid, and in fact it's the way the centroid is defined, so here's the centroidal axis that we're interested in, is that the first moment of area about that axis, so the first moment of area about the axis which goes through the centroid, is equal to 0. So let's draw out the equation which gives us the access to y bar. So the first moment of area of rectangle 1, so remember, first moment of area is area times distance from some axis, and it's the red dotted line in this case, to the centroid of that shape. Same thing for rectangle 2, and that must be equal to the total area times by y bar, where y bar is the thing we're trying to find. So we know everything but y bar, so let's put all of those numbers in. And if we multiply all of that out, we find that, according to my calculations, y bar equals 197.2 recurring millimeters. So next up is to find the second moment of area about this red line which goes through the centroid of the section. I'm going to call it ZZ because it's parallel to the Z axis and it goes through the centroid, which we now know is 197.2 millimeters from the bottom. The way we're going to do this is using the parallel axis theorem, which states, and it's a bit of a mouthful, that if we know the second moment of area of some components of the total shape about axes which are parallel to the one we're interested in, then we can figure out the whole second moment of area by adding together each of the individual second moments of area plus some extra terms which take account of the fact that the axes aren't on top of one another, for the sake of not being able to think of a better way of saying it. So probably the best way to demonstrate it is just to show how each of those terms is built up. So the total IZZ is equal to some contribution from that top rectangle. So the contribution here is equal to the second moment of area about the green dotted line for the top rectangle. So that's B, which is equal to 250 millimeters, times D. So D is always the distance which is perpendicular to the axis that you're interested in, cubed over 12, plus the parallel axis term, which is equal to the area of the shape, so that's 50 times by 250 times by the distance away from the distance between the two axes squared. So in that case this is 77.8 millimeters, because that's how far the centroidal axis of the top rectangle is away from the global centroidal axis. So we've got 77.8 squared, and we can do the same for the other rectangle, and hopefully, if I've calculated this correctly, the value is a whopping 2.061 times 10 to the power 8 millimeters to the power 4. So now it's time to calculate the shear stress. I've put the equation there for shear stress, S times by AY bar divided by IB. It's one of those equations where it's really important to understand what each of those terms mean, because the letters themselves, if you just remember that equation, may not help you to actually make the calculation. The key thing to calculating shear stress is to draw a line along the section which is perpendicular to the direction in which the shear stress is acting, and along which shear stress is equal. So for example, a line across here, the shear stress at everywhere along that line is equal. Okay, and the AY bar term in the equation corresponds to the first moment of area of the shaded bit, so the area on the other side of the pink line from the red line, from the centroidal axis. Capital S is the shear force, which is 80 kilonewtons in this case. I is the I value we've already calculated, and B is the length or the breadth of the line that we've drawn. So in this case B would be equal to 250 millimeters. So it's crucial that you remember about drawing the line and making the shading, and the Tor value that we come up with eventually would be at a distance y away. So it's the how far away the line you drew is away from the centroidal axis. Now the question asks us not for the shear stress in the top bit, which is on the small side, but for the shear stress in the web, in the sort of downstand bit, which is the most significant value of shear stress in the section, for reasons which will become clear later on, but which are all to do with this term B. Now, two choices here. One would be to draw this line that I've just talked about somewhere in here. So it's on the flange, sorry, on the web, and then shade the area above it. Sorry, it's getting a bit messy. Okay, that would lead to the right answer. There's no question about that. I'm going to call this the distance y. The only snag with that is that we would have to calculate this AY bar term for the shaded area, and the shaded area now has this shape, okay, which is just a bit more messy because there's two rectangles involved. Not impossible, but just a little bit messy. So if time is of the essence, it would be smarter to draw your line along the bottom part of the flange, shade on the other side of it, and we've got a simpler shape to deal with. So that's what we'll do here. Okay, so now we've got this diagram, we can start to build up the equation for shear stress. So in this case it's equal to 80 kilonewtons, I'm going to turn that into newtons, times by AY bar. So you have to remember that AY bar refers to that shaded pink section there. It's the first moment of area of the pink bit, pink shaded bit about the red line. Okay, so in this case Y bar is the distance down to here, and the area is the area of the shaded bit. So how to calculate the area? Well, it's going to be a function of y, because the pink line we originally drew is a distance of y away. But hopefully you can see that the breadth of the area here is 50 millimeters. Hopefully that's clear enough. And then this distance here is equal to 197.2, because it's a function of where the centroid is, minus y. So that's the area. The y bar bit, well, we would build that up from the fact that we know that to get there you've got to go some distance y, and you've got to go further on by this distance, which was 197.2 minus y, but half of that distance. So I'll put all of that into the equation. So that's the top line of the equation sorted out. It's looking a bit complicated, but we can tidy it up a little bit. Bottom line, a little bit simpler. So I is the I value about the red ZZ line, which we've already calculated as being 2.061 times 10 to the power 8 millimeters squared. And B, well, B is the length of the pink line you drew. Okay, so it's the breadth of the section at the point we're interested in. So it's this distance here, 50 millimeters. So I'll tidy up a little bit. So that's what it looks like with a little bit of tidying up. These equations always work themselves out in the same way. So once you've done it once or twice, you'll find it easier to do it subsequent times. And the way those two brackets work themselves out, well, let's see how they look. They look like, and that's the that's the final equation there for Tor. So you see that it hasn't got any linear terms in y, so it's always a number minus something times y squared, and that's how it always is. And what that means is that the shear stress is always a maximum when y is equal to 0, And because of the way that y is defined, that's always on the centroid, so that's what we know and we expect. That's good. So we can see the maximum value of shear stress here is 7.4 newtons per millimetre squared. we see that it's a quadratic distribution, and we would also see that if we plugged in a value of y of 197.2, which corresponds to the bottom of the section, then we'd find there was a value of torr of 0 there. So that gives us everything that we asked for in the question, as well as what the maximum value is.